Okay, hi everyone. This is Ken 121, week number 12. Today we'll be talking about solving systems of linear algebraic equations in Python. So, what's a system of linear algebraic equations? So, let's start by taking a look at this example right here. It's just a couple of equations, algebraic equations, not differential equations. So, for example, here I have 2x minus 3y equals 5, x plus 2y equals minus 3. Right? And typically, you should be able to solve this system of equations using process of elimination, right? So you maybe divide this first equation by 2. So you get x minus 3 over 2y equals 5 over 2. Then subtract these two guys from each other. And then you get, y, coefficient multiplied by y equals a constant. You find y, you plug it back in to get x, right? And this is how you usually do it. And the logic for this process is fairly constant, right? There isn't a lot of innovation. You're just following basically a bunch of steps to do it to be able to solve any system of equations. So this process can be generalized for computational work using Python. So for example, if you want to repeat this a bunch of times, you want to do this process, but for 50 systems or 50 algebraic equations with 50 unknowns, you can do it using Python. And this is usually achieved using matrix or matrix algebra. So let's have a look here. Again, we're looking at this same example. And when solving any system of equations using matrices, you have to define 3 matrices first. First one right here on the left-hand side is the coefficient matrix. And let's take a closer look at this coefficient matrix. What does it include? And as you can see here, it just includes the coefficients in your system of algebraic equations. So if this is the system of algebraic equations I'm referring to, this is just the coefficients put in a matrix. So first row here is 2 minus 3, which are the coefficients of the first equation here. Second one is 1, 2, which are the coefficients of this equation here, right? And this will be the first matrix you have to define when trying to solve a system of algebraic equations using matrices. Second matrix is the constant matrix, right? And I'm looking at the matrix in the middle here, the constant matrix. It has two numbers, 5 minus 3, and these two numbers represent the constants on the right-hand side of your equations, okay? So I need to first put all the coefficients in a matrix here called the coefficient matrix, put all the constants in a matrix here called a constant matrix, and then I put these two matrices next to each other, and this is called an augmented matrix. And I'm looking at the right-hand side here. This augmented matrix is basically your coefficient matrix, which is 2 minus 3, 1, 2, right? And 5 minus 3 next to each other. And the augmented matrix is just a coefficient matrix augmented by the constant matrix, right? So I'm just writing these two guys next to each other. You can include this line. It's just sort of a divider in as a visual aid, really. But what the augmented matrix contains is that it contains all the essential information about the system. It has everything except, the x's and the y's. I don't put them here. It only has the numbers, your coefficients and your constants. And this is really the starting point to solve systems of linear algebraic equations in Python. This is the basic logic to do so. So the objective of this lecture will be to learn how to manipulate this augmented matrix to solve a system, if assuming a solution exists, right? Sometimes, I'm sure you've taken this in your Calc 1 course, where sometimes you have a system of equations and there is no solution for a bunch of reasons. You can go and revise this. It's not part of this course. But basically, once you set up your augmented matrix, you need to manipulate it to be able to find the solutions. And ultimately, the manipulation should transform your augmented matrix into this form where I have 1, 0, 0, 1 is equal to m, n, where m and n are the solutions to your first and second equation, right? variable or equation, right? It's the same thing. Okay, so again, let's just repeat this quickly. If you have a system of linear algebraic equations, 2x minus 3y equals 5, x plus 2y equals minus 3. To start solving it using matrices, the logic is to create a coefficient matrix here, which is just a matrix containing your coefficients, a constant matrix here, which is a matrix containing your constants, and an augmented matrix. Basically, I just lump these two guys together to get an augmented matrix. And ultimately, you want to perform manipulations on this matrix to reach this form where I have a 1, 0, 0, 1 in my coefficient matrix, and then Mn in place of the constant matrix, and M and N are the solutions to the linear algebraic equations. Okay? So in a generalized type of form, if you are given a system of linear algebraic equations of the following form, a11x1 plus a12x2 all the way to a1n xn is equal to b1, and this is repeated, all the way to am1x1, am2x2, all the way to bm. Could be a system of 30 equations, 30 unknowns, 2 equations, 2 unknowns, 500 equations, 500 unknowns. This is the generalized form, right? Where x's are your unknowns, right? X's are the variables. A's are the coefficients. So A's are the constant numbers, or the coefficients, sorry, for these variables. So this could be 3x1 plus 2x2 all the way to minus 5xn is equal to 12, whatever. And B are the constants, okay? So if you have a system of linear algebraic equations of this form, you will need to or basically this system of linear algebraic equations is equivalent to a matrix equation of this form, right? Ax equals b, okay? So this system of linear algebraic equations is equivalent to this matrix equation of Ax equals b, where A is the M and N matrix of your coefficients, right? Let me write here of your coefficients. X is a column vector with n entries, and this represents your variables. And B is a column vector with m entries, and this represents your constants, right? So I have A, X, B. A is all your coefficients, A11, A12, all the way to AMN. X is all your variables, X1, X2, all the way to Xn, and B is all your constants, okay? So if I zoom back a bit and just compare these guys together, this is your system of equations, a11x1, a12x2, all the way to a1n xn is equal to b1, and you have m number of rows until you get am1x1 plus am2x2, all the way to amn xn is equal to bm. This system of equations is equivalent to this matrix equation where I have ax is equal to b, where A is a matrix containing all the coefficients in these systems of equations. So when you're writing A, you're only looking at the left-hand side, all of these equations, right? A11, A12, A1n, A21, A22, A2n, all the way to AM1, AM2, AMN. This only contains the coefficients, right? Okay, X is just your variables. They could be X1, X2, Xn. They could be X, Y, Z, K, J. It could be A, B, C, D. Whatever, just the variables you're solving for. And B is your constants, which are the numbers on the right-hand side of your system of equations. So in order to solve this matrix equation here, in order to solve this matrix of equation, X, basically we're solving for X. X is equal to inverse of A multiplied by B, right? X is equal to A to the minus 1B, inverse of A multiplied by B. So now when you think about how to do it in Python, you have a system of equations, you create your matrix containing the coefficients, you create the matrix containing the constants. You want to find the solution, you just multiply the inverse by B. Multiply the inverse of this matrix here by this vector here, or 1 by m matrix. Okay, and A is the inverse of A. It's important for you to remember this, and recall from last week what the inverse is. We talked about this last week, so you can go back and listen to the lecture or remember it, or read about it on Wikipedia or any other resource. But basically, an inverse of A is 1 over the determinant of A22 minus A12 minus A21, A11, and the determinant of A cannot be equal to 0. So last week, a couple of you guys emailed me about this. Determinant of A is a very small number, and the inverse of A is a very large number. It's because if you verify your calculations by hand from last week, you're going to find that the determinant from last week's example was actually equal to 0, but Python will not give you 0, right? It will give you a very small number. This is due to just how it stores information. So that's why it's always good to verify by hand, or at least have a feel for these things. If it's 10 to the minus 16, it's 0, and there is no inverse. If there is no inverse, this system of equations does not have a solution. Okay? So just to revise this thought, if you have a system of linear algebraic equations, I'm going to create two matrices. First one is A, containing all the coefficients. Second one is B, containing all the constants. And then to find the solution of these equations, I multiply the inverse of A by B. Okay, so let's try to do an example in Python now. Okay, so let's say in Python, you're being asked to solve the following system of equations. Okay. First one is 4x plus 3y is equal to 20. Second one is minus 5x plus 9y is equal to 26. This is a simple one. You can do it by hand and get a solution. However, now we're going to do it by using Python. Okay, so let me just copy these equations to Python here. Let me switch to Python first. Spider. Here we go. And these are the equations, right? Let me zoom in. So you want to solve the following system of equations, right? Okay. And we're going to follow the same logic, but in Python, we're actually using the NumPy library. So again, first thing we need to import our libraries which we're going to use. So I'm going to start off, my first command here will be import NumPy as NP. Okay, this is the first thing I need to import. Oops, this is NumPy right here. No, NumPy. Here we go. Import NumPy as NP, and this will be the library I'm using to solve these matrices. Okay. First step will be I need to create the matrices I need, and the first one will be the coefficient matrix. And I use the terminology A for the coefficient matrix and B for the constant matrix. Feel free to use whatever you want as long as you're doing the math properly. And A will be NP dot array, right? And it will be the coefficients of the first equation 4, 3, 4, comma 3, and then comma here, another set of square brackets, coefficients of the second equation, minus 5, comma 9, right? And every equation, I have a set of square brackets. Basically, every row has its own set of square brackets, and I'm separating the elements with a comma, right? So 4, 3, minus 5, 9. This is the coefficient matrix. Okay, and then I'm going to create the constants matrix. And this will just include the two numbers 20 and 26. So again, I'm going to use b is equal to np dot array 20, 26. So now I have my coefficients and my determinant matrices. And in order to determine the solution of this system of equations, as we said, first of all, good practice for you when doing this is to always check the determinant, right? Check that the determinant of A is non-zero. And this is very important because if the determinant is zero, then your system does not have a solution, right? It's just a system of equations without solution. That's how it is. And if you recall from last week, to check the determinant, I'm just going to print it out directly. I use np.lin algebra, right? I need to use the sublibrary lin algebra dot determinant, or yeah, dot determinant of A, right? So I'm just checking that the determinant of A is not zero. So at this point, I'm going to run my script and look at the determinant of A in my shell on the right-hand side here. So let's run it. Just not happy about something. Let's see. Field elements must be 2 or 3 tuples. Got -5. Okay. Let's see. Okay, yeah, we're missing another set of square brackets here. Just be careful with this. When creating an array, you need normal brackets and then square brackets, and then in the square brackets, you start listing your rows, each row with its own set of square brackets, okay? So this is a common mistake I think we also did last week. Just don't forget about the second set of square brackets here. Let's run this guy. Good, so when we run it, we get that the determinant of A is 51, right? And 51 is non-zero, so we can go ahead determining the solution. Okay, so it's non-zero, so what I'm gonna do is now I'm gonna find the inverse of A, and I'm gonna save it in the variable inverse A is equal to np.lin algebra dot in A, right? And we talked about this last week, how to get the determinant, how to get the inverse, and go back and revise it. Okay, so now to get the solution, we said we'll multiply the inverse of A by B, right? Multiply inverse of A by B. And this is how we determine the solution for the system of equations. So I'm going to say x is equal to np dot lin algebra right, np dot lin algebra dot inverse of A dot B, right? And what I'm doing here is I'm just rewriting this line here to get the inverse of A. So if you don't want to create this intermediate variable, you can just do it directly this way. And let's print x to see the results for this system of equations. And you're going to get the solution is 2, 4, right? This is the result of your system of equations. And if we go back to just to check it, 2, 4, does this work? 4 multiplied by 2 is 8. 3 multiplied by 4 is 12. 8 plus 12 is 20, so that's fine. Minus 5 multiplied by 2 is minus 10. Plus 9 multiplied by 4 is 36. Minus 10 plus 36 is 26. So this solution is correct. So going back here, if you don't want to use this entire expression and just use this variable, it should be the same, right? If I just use inverse A and run it, should get the same thing, right? So it's up to you if you want to create a separate variable where you save the inverse of A in it and then use this variable, or if you want to just, not write this variable at all and just put the form to determine the inverse and multiply it by b directly, it's going to achieve the same thing. It's just a matter of saving or not saving. Okay, so this is how you determine the solution for systems of linear algebraic equations. There is another way to do it. So if you don't want to do this, there is sort of another way, just for your information. You can use XP lin algebra. Then you can write solve a comma b, right? So if you write solve a comma b, this will also determine the solution for this system of equations. So if I write x is equal to np, so np.linearalgebra.solve a comma b, and let's differentiate them. So I'm going to call this x1. And then if I print x1, I should get the same answer as this guy, right? You get 2, 4 using the first method and 2, 4 using the second. And these are two ways to solve a system of linear algebraic equations. You know, it's a very useful method. So especially once you go into your other courses and you have, maybe you want to solve, you know, conversions and reactors, you want to solve some math balances, whatever, being able to format them this way and just solve them all at once is a good thing, is a good tool to have. Okay. All right, let's go back to the Word file. And so the script is pasted here as well for your reference. Where first of all, we import, we create the coefficient matrix, we create the constant matrix, check the determinant is non-zero, find the inverse, and then this determining the solution of the equations using two methods. First one is multiplying the inverse by the constant matrix, or just using the solve command to find it. All right, so for next week, before next Monday, and let me just, Monday will be April 19th, right? By 12 p.m. If you need more time, just send me an email, but let's aim for 12 p.m. Determine the solution of the following systems of linear equations in Python and verify your results with hand calculations. Okay, so you have 5 problems here, solve them all using Python. This is going to be very quick in Python, right? And verify them with hand calculation. Submit a report showing your handwork, script, and commenting on any discrepancies. And please pay attention to the way you organize your report, you organize your results, and the way you present your results. Okay. So before ending this lecture, let's just do one together, a 3x3 one, because the example is 2x2. So let's just do a 3x3 one together. So I'm going to do the first one here, and I just copied the system of equations, and now I'm just going to go to Python to paste them. So let me just paste them here. And if you have the script written for one of them, you just need to change a script for any set of equations. So here I have 8x 3y minus 2z 9, minus 4x 7y 5z 15, 3x 4y minus 12z 35. So what I'm going to do is I'm just going to change the coefficient matrix to include these coefficients. So my coefficient matrix will, first row it has 8, 3, minus 2. So I'm going to change this guy to 8, 3, minus 2. Second row here is minus 4, 7, 5. I'm just going to change this guy to minus 4, 7, and then 5. And then I have a third row here. So third row means a new set of square brackets. And this third row here will have 3, 4, minus 1, right? So this is my coefficient matrix. 8, 3, minus 2, coefficients first of equation. Minus 4, 7, 5, coefficients of the second equation. 3, 4, minus 12, coefficients of the third equation. Constant matrix now becomes 9, 15, 35, right? This is the constant matrix. I just list the constants next to each other in a matrix, okay? And then the rest of these will not change, right? You just change your coefficient matrix, just change your constant matrix. That's why doing it in Python makes it easy to generalize the process. You can do this very quickly, you can determine the solution very quickly. And if you run it, you're gonna get the solution right here, minus 0.53, minus 1.9. And this is the solution for these three systems of equations, right? So please do this for your homework. And again, if you forgot how to do it by hand, you do it through a process of elimination, okay? So just a quick, I guess a quick reminder. You can start with the two top equations and eliminate one variable. Let's say I want to eliminate x. So I'm gonna multiply the second row by minus 2, right? So if I multiply this row by minus 2, I'm gonna get minus 8x plus 14y plus 10z is equal to 30, right? We just multiply this row by minus 2 here. And then if I add these two guys together, and then if I add the first and the second equation, I'm gonna get what? I'm gonna get 17y plus 8z is equal to 39, right? So now I have just an equation of y and z. I eliminated x. You can do the same with the first one and the third one to get a second equation with just y and z. And then you can do the same with the y and z equations to get maybe one equation with only z. And then you solve this equation to get z. Once you have z, you plug it back in here to get y. Once you have z and y, you plug it back here to get x. Okay? And you should have covered this in your elementary math courses. You know, if you forgot to just take a minute and revise them, it's not that hard. Just be patient with the algebra and don't get frustrated too easily. Okay, that's it for today. Thank you very much. I'll see you next week.